Good morning, all of you. In today's class, we will learn second law of thermodynamics and quasi-static process. So let's start. Second law of thermodynamics. We have learned zeroth law of thermodynamics, first law of thermodynamics, and now this is second law of thermodynamics. So in this, you are having two statements of two different scientists. This second law are having two statements of two different scientists, we can say. What are those? Let's see. First one, I am taking Kelvin Planck statement. What is first one? Kelvin Planck statement. So see what they are saying. No process is possible. No process is possible whose sole result, sole means net result, okay? Whose sole result, whose sole result is no process is possible whose sole result is absorption of heat from a reservoir and the complete conversion of heat into work, and complete conversion of heat into work. What is the meaning of this? Let me explain. So you see here, suppose you are having a machine, right? This is a machine. Okay, listen carefully. This is a machine, and now it has absorbed, let us suppose, 100 calorie heat. Okay, how much absorbed? Absorbed 100 calorie heat, this machine. And now if this machine is doing work of this, because heat is going to convert into work, so this work will be something 80 calorie, not 100 calorie. Understand? Because complete absorbed heat, this machine will not work of 100 calorie. Understand? If it is absorbing 100 calorie, work will be always less than 100 calorie. It will be never equal to 100 calorie. That is what complete absorbed heat is not possible to convert into work. Understood my point? Is that clear? Okay, this is what the meaning of this statement. Okay, next. This is what we have learned, Kelvin Planck statement. Next one, that is Clausius statement. Next one is what? Clausius statement. But before that, one more line I want to give here, that is, or 100% efficiency is not possible. Yes or not? 100% efficiency is not possible. Or 100% conversion of heat into work is not possible. You can write like this also. Choice is yours. Same meaning, means how much we have absorbed, that much we cannot convert into work, isn't it, right? So you write like this, or 100% conversion of heat conversion of heat into work is not possible. Already I have explained, right? So this is your Kelvin Planck statement. Next one, that is Clausius statement. Clausius statement. What this scientist is telling us. Let's see. So listen here. What he is saying. No process is possible. No process is possible whose sole result is the transfer of heat from a colder object to from a colder object to hotter object. Yes or not? We know heat transfers from hot object to cool object. But is it possible to transfer from cold object to hot earth? No. This is ice. This is a cold object. And here is a fire, or it is at 100 degrees Celsius. Will it transfer from this to this? No. It will always flow from hot to cool. But it is not possible to flow from cold to hot. Understand? This is what the meaning is. Cold to hot is possible. Understand? That is what the meaning of this statement. That is what Clausius statement. It is not possible to transfer of heat from colder object to hotter one. This is what the second law of thermodynamics, and these are the two statements given by different scientists. Okay. So these two statements are equivalent to one another. These two statements of second law are equivalent to each other if one is violated, automatically other is also violated. The other is also automatically violated. Okay. So these are the two statements they are asking you sometimes for 2 marks, state second law of thermodynamics. That time you have to write these both statements, right? It is very simple. First one is Kelvin Planck statement. No process is possible whose sole result is absorption of heat from reservoir and complete conversion of heat into work, or 100% conversion of heat into work is not possible. Clausius statement, no process is possible whose sole result is transfer of heat from colder object to hotter one is not possible. And this is general line I have written below. That is what these two statements of second law are equivalent to each other. If one is violated, definitely another is also violated. Got it? Understood? Note down. Note down fast. Okay, finished. Let's move ahead. Now, next topic, that is quasi-static process. This is what we have finished now. Second law of thermodynamics we have finished. Now, next one, that is quasi-static process. Quasi-static process. What is this quasi-static process? See here, this quasi-static process is nothing but it is very slow process in which at each and every point the system and surrounding will be in thermal and mechanical equilibrium. Understand? In one line I have told you. So I am giving you some points. Let's see what is this quasi-static process. So see here, it is an infinitely slow process It is an infinitely slow process in which the system remains in thermal and mechanical equilibrium. System remains in thermal and mechanical equilibrium with surroundings at each and every intermediate state. Okay. For example, let me explain in general language. We can say one general example. You know, pump, air pump. You know, cycle. We are filling air. No, air pump. How it is? Listen here. Like this pump will be, yes, something like this, and there will be one pipe for filling the air, isn't it right? Like this, something rough diagram. Try to understand. And here will be one piston, okay, and there will be one handle like this to press this air, okay, like this. So here is one small hole to take air inside from outside one. Okay, that hole is not necessary for us now, right? So like this pump, and now what you do, you just move this piston very slowly, very slowly. Move piston very slowly, very slowly, very slow. The air which is coming out of this pipe will have same pressure with the surrounding. Understand? Just move it down very slow, and you just see whatever the air pressure outside and which is coming out from this pipe will be same. Then can I say that this is also quasi-static process? If I am moving this piston very slow. Understand? That is what the meaning of this quasi-static process is. It is a very slow process, and at each and every intermediate state, the system and the surrounding are in thermal and mechanical equilibrium. So already I told you this mechanical equilibrium means no unbalanced force, and thermal equilibrium means the temperature is same. Isn't it right? Already we have learned these definitions. Go back those who don't know. See the notes, right? So this is what general example I told for this quasi-static process. And for example, already I told, then also I'm writing here. For example, consider a system of gas or just I can write like this. For example, system of gas contained in a cylinder fitted with movable piston. This is what the example of this quasi-static process. Some points I am giving about this quasi-static process. So see here, one more point. If the piston is pushed very rapidly, I will draw one diagram also for you here. Okay, so that you will understand this quasi-static process. This is, you can see the piston and the cylinder, and here is a gas. This is what example of this quasi-static process. So see, if the piston is pushed very rapidly, what happens? If the piston is moved very rapidly, rapidly means what? Very fast, immediate action. The gas immediately acquires kinetic energy if the piston is moved very rapidly. The gas immediately acquires kinetic energy which is behind the piston, and is set into turbulent motion and is set into turbulent motion. Turbulent motion means what? Not if suppose this is a pipe, see the one which is when it is coming out of this pipe, how it is something like this. But when it is inside the pipe water flow, this is what laminar, but this is turbulent, like this turbulent motion means. Okay. So is set into turbulent motion, which is non-equilibrium state. Yes, which is non-equilibrium state. Non-equilibrium means there is some unbalanced force. That's why not in equilibrium. Equilibrium, non-equilibrium state. So in this case, work done is not quasi-static. Work done is not quasi-static and not governed by dw is equal to p dv. So we cannot use this equation if this system is like this, right? Next point, one more. What is that? C. If the piston is pushed very slowly, if the piston is is pushed very slowly, the system is at all times in a equilibrium. The system is at all times in a equilibrium. And then the process can be considered as quasi-static. Then the process can be considered as quasi-static. So in this process, as already I told, in this process, the system passes through number of states. System passes through number of states which are thermodynamically in equilibrium. Which are in equilibrium, right? So this is what quasi-static process is. So we have learned today second law of thermodynamics and quasi-static process. So second law of thermodynamics, you are having two statements, that is Kelvin Planck and Clausius statement. Next one we have learned this quasi-static process. This quasi-static process is an infinitely slow process in which system remains in thermal and mechanical equilibrium at each and every intermediate state. For example, and some points we have taken. So these two are very important for IP point of view. Sometimes they are asking for 4 marks or sometimes they are asking for 2 marks. So try to understand, read carefully and slowly you read, not an issue. It is very small topic I have finished, right? So try to revise once if you will get time. If you have doubt, just call me, okay? And just read, okay? So we'll stop here. Bye for today.